Hello, welcome back to the channel. So let's continue our discussion on solving improper integrals. And in this video, we'll know the strategy or the steps required in order to solve improper integral with unbounded integrand. But before watching this video, I will highly suggest you to first watch my previous videos in order to get the full context of this video. So what we mean by unbounded integrand is, you remember we covered two cases when we call a definite integral as an improper integral. The case of unbounded integrand is basically the second case whenever you're solving a definite integral which has a point of discontinuity in between the interval specified in the definite integral. As you can also clearly see in this example as well, you can see that this function is not defined at x equals 1, right? But you have x equals 1 in the interval. So this is an improper integral which obeys the second case. So that is why we require another way in order to solve these type of integrals which have point of discontinuities in between the interval specified for the definite integrals. And again, similarly, like the cases of the infinity bounds, we have three cases for solving improper integrals with unbounded integrand. So solving these type of integrals involves the knowledge of limits, especially the left and right hand neighbors of a number. Don't worry, we'll cover the concepts in brief in this video. And again, just like the previous two videos, this video will also be divided into two parts. In the first video, we'll cover the concepts which we should know in order to solve these type of questions. And in the next video, we'll solve this question by using all the concepts that we'll cover in this video. So now, let's cover the case 1. So the case 1 is whenever you're solving a definite integral which has a point of discontinuity at x equals a, what you will do is you will consider a new variable small t which lies in between the interval a and b, and then you will solve this definite integral first. And after you are done with solving this definite integral, you'll take the limit of t approaches to a plus. And what we mean by a plus is basically the right hand neighbor of a, right? I'm sure you would already know the concepts of left hand and right hand neighbor. So if you have a point which is, for example, a, this is a plus is basically the right hand neighbor. If this is the number line, a plus is the right hand neighbor of a, and a minus is basically the left hand neighbor of a. And these a minus and a plus are considered to be very close to a. So a minus is basically approaching a from the left hand side, and a plus is basically approaching a from the right hand side. The only important point about these a minus and a plus is that they are very close to a but not equal to a. So by using all these concepts, by using the concepts of solving limits, you'll basically solve the solution to this definite integral. So again, summarizing it all, if you are calculating the definite integral of fx dx, where fx has a point of discontinuity at x equals a, what you will do is basically you'll consider a new variable small t which lies in between a and b, and you'll solve this definite integral first. And after solving this definite integral, you'll take the limit t approaches to a plus. So this is what we do when we have definite integrals which follow the case 1. Similarly, there are two other cases which will require the same concepts. The second case is whenever you are solving a definite integral which has a point of discontinuity at x equals b. So basically the upper endpoint. The first case was about the lower endpoint, right? The second case is whenever you are solving the definite integral of fx dx which has a point of discontinuity at the upper endpoint, which is x equals b, you'll follow the same concept. So what you'll do is you'll consider a new variable, again capital T. The variable symbol doesn't matter. You can take capital R or capital Z as per your choice. But the concept is you'll consider a variable which lies in between the interval a and b, similarly as in the case of case 1. And what you'll do is you'll first solve this integral, and then in this case you'll take the limit of capital T approaches to b minus. So you'll take the left hand neighbor of b in the second case, right? And then you can have the third case in which you have a point of discontinuity which lies in between the interval a and b. For example, in the case 3, you know that your definite integral interval is a to b. So if you have a point of discontinuity which is at x equals c, where your c lies in between a and b, what you'll do is, you know that in definite integrals you can always break the definite integral. So the definite integral from a to b of fx dx can be easily converted to integral a to c fx dx plus integral c to b for fx dx, right? We know that we can always break this definite integral into these two parts such that for these definite integrals, for one definite integral we have a discontinuity at the upper endpoint, and for one definite integral, we have a discontinuity at the lower endpoint. And then we'll use basically the same concepts that we covered in the case 1 and case 2 in order to solve these two definite integrals over here. Don't worry if that seems complicated. We'll solve this question in the next video, which will give you a detailed idea about how to solve improper integrals with unbounded integrands. So stay tuned for that. Also, feel free to comment down in the comment section below if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.